Hi viewers, a warm welcome to all. This module focuses on biocompatible nanomaterials and their applications. First of all, nanotoxicology. This is a term which is related to biocompatibility of nanomaterials. Nanotoxicology is a new field that evaluates the toxicity of nanoscale materials on the health of organisms. It is the application of toxicology to nanoscience. The term nanotoxicology was coined by Oberdoster in 2005. According to Oberdoster, nanotoxicology is the science of engineered nano devices and nanostructures that deals with their effects in living organisms. Nanotoxicology explores the effect of exposure of different nanomaterials. Because of quantum size effect and large surface area to volume ratio, nanomaterials have unique physical properties that affect their toxicity. Properties that affect toxicity. Nanotoxicological studies are intended to determine whether and to what extent the properties of nanomaterials may pose a threat to the environment and to human beings or animal beings. Size is a key factor in determining the potential toxicity of a nanoparticle. However, other properties also influence the toxicity of nanomaterials. Important properties of nanomaterials that affect their toxicity are shown in this chart. Nanotoxicology determined by surface area of nanoparticles, morphology of nanoparticles, chemical composition, size of the nanomaterial, surface charge and solubility. Let us check one by one factors. First of all, size. Size is a key factor in determining the potential toxicity. The smaller a particle, the greater is its surface to volume ratio and the higher is its chemical reactivity and biological activity. Next one, chemical composition. The toxicity of nanoparticles depends on their chemical composition but also on the composition of any chemicals adsorbed onto the surface of the nanomaterial. In certain cases, the nanoparticles may be contaminated by some other chemicals. Such chemicals also determine the toxicity. Another factor is morphology. Health effects of a nanoparticle are likely to be depend on their morphology. Surface area. The greater potential hazard may relate to the surface area of nanoparticles compared with that of the same mass concentration of larger particles. Another parameter is surface charge. The aggregation of nanoparticles with biological materials may depend on the charge on the surface. Solubility is another concern. Poorly soluble nanoparticles can exhibit more pronounced toxicity. Disease due to nanoparticle exposure. It should be noted that all nanoparticles are not toxic, but many nanoparticles are toxic and they affect adversely different parts of the human body, leading to different diseases. For instance, in brain, nanoparticles, toxic nanoparticles may cause neurological diseases, Parkinson's disease or Alzheimer's disease. For lungs, nanoparticle agglomeration may cause asthma, bronchitis, emphysema, cancer. For circulatory system, arteriosclerosis, vasoconstriction, thrombus, high BP, and from the picture, it is clear that nanoparticle toxicity may adversely affect different parts of the human body, leading to different type of diseases. Now, we can enter into biocompatible nanomaterials. What is biocompatibility? Biocompatibility is a general term describing the property of a material being compatible with living tissue. Biocompatible materials do not produce a toxic or immunological response when exposed to the body or body fluids. The term biocompatibility refers to the ability of a material to perform with an appropriate host response in a specific situation. Definitions of biocompatibility. Several definitions are in practice. Some common definitions are the quality of not having toxic or injurious effects on biological system is one common definition. Another one is a definition by Williams. The ability of a material to perform with an appropriate host response in a specific application. This is the most widely accepted definition of biocompatibility. Biocompatibility is the capability of a prosthesis implanted in the body to exist in harmony with the tissue without causing deleterious changes. Biocompatible nanomaterials. A nanomaterial which satisfy the requirements of biocompatibility, the conditions of biocompatibility, is termed as a biocompatible nanomaterial. Such biocompatible nanomaterials are known, and examples include nanocrystalline hydroxyapatite, silica, gold nanoparticles, natural polymeric nanomaterials such as chitosan, synthetic polymer nanomaterials like polylactic acid, and many other. First of all, nanocrystalline hydroxyapatite. Hydroxyapatite can be denoted as HAP. Hydroxyapatite has the molecular formula Ca10PO4 6 times OH twice. It is the main constituent of biological tissues such as our bone and teeth. HAP is an ideal green natural material with excellent biocompatibility and biodegradability. It is a very important biodegradable substance. Nanophase hydroxyapatite possesses unique properties such as high surface to volume ratio, reactivity, and biomimetic morphologies compared to the bulk hydroxyapatite. Regarding the synthesis of nanocrystalline hydroxyapatite, there are various methods for the preparation. Such methods have their own advantages and disadvantages. Let us have a look on the common methods employed for the synthesis of hydroxyapatite or nanocrystalline hydroxyapatite. We can have wet chemical synthesis, dry synthesis, and high temperature synthesis. There are several morphologies for nanocrystalline hydroxyapatite. It should be noted that the size, morphology, and the degree of crystallinity depends on the method adopted for the synthesis as well as conditions of the synthesis. Hydroxyapatite nanocrystals can have different morphologies as shown in the picture. It may be nanospheres, nanospindles, porous nanospheres, it may be nanoflower, nanoflakes or nanorods, which means hydroxyapatite nanocrystals can exhibit this type, any one of this type of morphology. Classification of nanocrystalline hydroxyapatite based on the functional properties, that is functional properties like luminescence, magnetism, etc., and their utility in biomedical applications. It is possible to classify hydroxyapatite nanocrystals. Based on such classification, there are three types of nanocrystalline HAP. These three main types are designated as luminescent hydroxyapatite, magnetic hydroxyapatite, and luminomagnetic hydroxyapatite nanocrystals. First of all, luminescent hydroxyapatite nanocrystals. Remember, hydroxyapatite as such has no luminescent properties. However, incorporation of at least one fluorescent moiety or fluorescent label in the hydroxyapatite matrix enable the formation of luminescent hydroxyapatite nanocrystals. How we can convert hydroxyapatite to luminescent hydroxyapatite? There are different possibilities. Some chances are incorporation of luminescent metal ions like lanthanide ions, and dyes, several type of compounds that can provide luminescence can be incorporated to nanocrystalline HAP to make them luminescent. Magnetic hydroxyapatite nanocrystals. It should be noted that hydroxyapatite as such has no prominent magnetism. It is diamagnetic. However, incorporation of paramagnetic, ferromagnetic or super paramagnetic labels into nanocrystalline HAP enables the formation of magnetic hydroxyapatite. So, it is possible to make hydroxyapatite magnetic by incorporating some metal ions, iron oxide, iron or cobalt, etc., as detailed in this picture. Now, luminomagnetic hydroxyapatite crystals. Look on the name. Luminomagnetic, which means combination of luminescence and magnetism. Two properties together, two functional properties together. Hydroxyapatite nanocrystals with simultaneous luminescence and magnetism is termed as luminomagnetic hydroxyapatite. To get it, incorporate fluorescent and magnetic labels in nanocrystalline HAP. The important advantage of such bifunctional means two functional properties, means luminescence as well as magnetism in a single system can be highly suitable for biomedical applications. This strategy of bifunctional molecules developing always helps in multimodal imaging probes. Now, another type of biocompatible nanomaterial, it is nothing but silica nanoparticles. Silica nanoparticles are optically transparent, it is of low toxicity, inert to pH and degradable. Not all, some of them are degradable. More attractively, their surface can be easily functionalized. That means it is possible to introduce different functional groups on the surface of the spherical silica nanoparticles. The surface functionalization is possible through well-established silane technology. Silica nanoparticles have broadest range of accessible sizes and can be synthesized as uniform particles within the size range of 5 nanometer to 2000 nanometer. There are two major types of silica based nanoparticles. They are solid silica nanoparticles denoted as SINPs and mesoporous silica nanoparticles denoted as MSNs. Picture represents the TEM image of solid silica nanoparticle and mesoporous silica nanoparticles. There are several methods for the synthesis of silica nanoparticles. However, the most common method is the Stauber method. The Stauber method is highly established method which is an easy method for the synthesis of nanoparticle. The nanoparticles here are formed via a sol-gel process. The reaction, that is the Stauber method, involves the reaction which is hydrolysis and condensation of silicon alkoxide, preferably tetraethyl orthosilicate, in the presence of a catalyst. The reaction can be catalyzed by mineral acids such as hydrochloric acid, base such as ammonium hydroxide or ammonia solution. Figure illustrate the generation of silica nanoparticle based on the Stauber method. Now, the produced nanoparticle can be functionalized by different methods. Functionalized silica nanoparticles are highly adaptable for several biomedical applications. They are easily chemically modified due to reactive hydroxyl groups on the surface and can be impregnated easily with dyes and different fluorescent labels. The easiest and most used method for the functionalization of the nanoparticle surface is the use of silane as anchor chemistry. Biomedical applications of nanomaterials. Biocompatible nanomaterials we have discussed. Such biocompatible nanomaterials found enormous applications in the biomedical arena. Let us have a discussion on important biomedical applications of nanomaterials. Owing to their favorable physicochemical characteristics, nanoparticles find large number of applications in biomedical field. Different nanomaterials are suitable for specified applications. Out of this, biocompatible nanomaterials are better candidates, better performers for in vivo applications. Two major applications of nanomaterials in biomedical field are the imaging application and therapeutic applications. This is mainly because of the fact that nanomaterials can overcome shortcomings such as difficulties, drawbacks such as short blood circulation time and non-specific biodistribution associated with traditional or conventional imaging and therapeutic probes. Some examples of biomedical applications: biological imaging using quantum dots, immunofluorescent biomarker imaging, target specific fluorescent imaging, immunogold labeling, targeted drug delivery using nanoparticles, gold nanoshells for immunoassay and cancer cell detection as well as therapy, carbon nanotube field emission multiplex X-ray array for microradiotherapy application. These are some important applications, biomedical applications of nanomaterials. The biomedical applications in general is pictorially shown here. The biomedical applications include generally drug delivery, therapy, gene delivery, biomarker mapping, molecular imaging, detection and diagnosis. First of all, molecular imaging. The molecular imaging aimed at non-invasive and quantitative visualization of molecular process occurring at cellular and subcellular levels. There are several imaging modalities. These include magnetic resonance imaging, MRI, X-ray computed tomography imaging CT, positron emission tomography PET, optical imaging OI and ultrasound imaging. Nanoprobes for bioimaging. Several nanoparticles are such employed for imaging purpose. This is by virtue of their features like luminescence and magnetism. For instance, gold nanostructures are highly useful in optical imaging due to their luminescent properties. Oxide nanoparticles like iron oxide, gadolinium oxide GD2O3 are used as contrast agents in magnetic resonance imaging technology due to inherent magnetism. Dye-doped silica nanoparticles can be used in optical imaging due to their prominent luminescence. Imaging applications of hydroxyapatite nanoparticles. As we are aware, hydroxyapatite can be functionalized, can be made luminescent or magnetic. They are highly biocompatible, and luminescent and magnetic hydroxyapatite nanocrystals can be used for several imaging applications. For instance, luminomagnetic, that is those with HAP nanocrystal with luminescence as well as magnetism, can be used for optical imaging, MRI, computer tomography, X-ray and SPECT imaging technology. Magnetic hydroxyapatite can be used in magnetic resonance imaging. Luminescent hydroxyapatite can be used in optical imaging including NIR imaging and upconversion imaging. Theranostic nanomaterial. The term theranostics is a combination of two terms, therapy and diagnostics. A nanomaterial which can be used in therapy as well as diagnosis is termed as a theranostic material. A theranostic material have associated antibody, contrast agents or drugs or many. That is, a single nanomatrix can be functionalized with different suitable agents for therapy as well as for diagnosis. Such materials are called theranostic nanomaterials or theranostic nanoparticles. Another important aspect of this module is to familiarize nanomaterial research in India. Our country is a place where enormous research occurring in nanomaterial field. Let us have a glimpse on various research institutions where nanomaterial research is more dominant. After the post-graduation, either MSc or MTech, in relevant subjects, it is possible to perform research in material science, that is simply nanomaterials, through necessary entry-level examinations. Since nanomaterial research involves need for advanced characterization facilities, it is better to have an awareness about pioneering nanomaterial research centers in our nation. In our country, there are several high-end research institutions where research can be performed on nanomaterials. Some pioneering institutions in India. Institute of Nanoscience and Technology, INST. INST Mohali, that is in Punjab state, is an autonomous institution of Department of Science and Technology, DST. It has been established under our nation's Nano mission, initiated by DST to boost research and development in the field of nanoscience and nanotechnology in India. Another institution is our Indian Institute of Science, IISc, where there is a Center for Nanoscience and Engineering, denoted as CENSE. CENSE was established to pursue interdisciplinary research across several disciplines with a focus on nanoscale systems. Center for Nanomaterials, CNM ARCI, International Advanced Research Center for Powder Metallurgy and New Materials, ARCI, is an R&D center of Department of Science and Technology. The CNM was established with a mandate to develop technologies for large-scale production of nanopowders and also to explore their utilization for different applications. Center for Nano and Soft Matter Science, CENS, is an autonomous research institute again under DST. Core support to center is provided by DST. Here there is applied science research in nano and soft matter science. It is located in Bengaluru. Indian Institute of Technology, IITs, are the most prestigious institution in our nation that offer technological education of international quality. At present, there are 23 IITs in our nation. Most of them offer high-end nanomaterial research under different areas of nanotechnology. They will provide advanced instrumental facilities for the researchers. Council of Scientific and Industrial Research, CSIR. Most of the CSIR laboratories in India offer nanomaterial research facility. In addition to many high-end research institutions and R&D centers like ISER, ISRO, BARC, TIFR, etc. offer material science research facility. In addition to such high-end institutions, our universities across the country has pivotal role in nanomaterial research. Thus, an idea about the research facility will assist you whenever you are seeking some research facilities in the field of nanomaterial science. That all about this module. Thank you all.